Hey, welcome back. This is the Web3 Idiot. Today we're going to be continuing our series on Facebook LeetCode questions. Basically what we're going to do is I'll explain the question to you and then do some coding and explain what's happening in the code. And hopefully you learn a bit. It allows me to improve my ability to talk my way through an interview question. And yeah, that's about it. So today we're going to be doing the for sum and remove nth node from end of list. Yesterday we did three sum closest and letter combinations of a phone number. If you remember, three sum closest is very similar to the three sum question here. And then over here, letter combinations of a phone number is just a classic backtracking question where we use a stack. And we're going to be doing pretty much the same thing with this for sum here. And then number 19, remove nth node from the end of a list. It's our first linked list question. It's going to be fun to do that. I did that before, as you can see, but we'll go ahead and get it done. Yeah, it looks like we're getting into the stack section. This is a stack question. This is a stack question, stack question, stack question. Merge two sorted lists, and I don't know. I know how to do that one, but yeah. Okay, we're gonna go ahead and get started. So let's move on to for sum. I have not done this one, but I have a general idea about how to do it. Given an array of nums with n integers, return an array of all unique quadruplets. Okay, so instead of returning sums, we'll be returning an array of the numbers such that a0 is less than or equal to a, b, c, d is less than n. Okay, so a, b, c, d are all distinct. So, okay. No duplicates. Sounds good. All right, so let's see. Basically, the same way that we handled the three sum and three sum closest, we're going to have to put this in order. Same thing with two sum. These all build upon each other. So if you have not done two sum, go back through two sum. If you've not done three sum, go back through three sum. And four sum is just very straightforward. We have to get to a point where we can use the same skills as we did before. And one way of doing that is with a recursive call. So we're going to go on and yeah, this is a backtracking question as well, combined with two sum. So let's go ahead and get sorted. So let sorted nums equal nums dot sort where a and b is a minus b. So that gets us an array of numbers. And then what do we want to do? We also want to initialize our output. Let output equal, and what are we doing an array? And then we also have to initialize our stack. So let our stack equal this. So this is another backtracking question. So we are using a stack. When we reach a certain criteria, we'll push the stack to the output and then pop items off and then continue on. One way of doing this is we know it's for sum. So we'll come up here, just get out of the way. If nums dot length is less than 4, it has to have at least 4 numbers in there. What we're going to do is return an empty array. All right, so here we go. We have our output, we have our stack, and what we want to do is implement a helper. So just like I did in the last video with number of combinations of word or letters you can make using a phone number. What we're going to do is have a helper. So we're going to have a function helper, and inside here we will be passing the number of elements left. We're trying to get down to the magic number of 2. So we'll start out here. We have k. We'll start out k equals 4. All right. What else do we need to pass in? Let's see. We have k equals 4. We need to pass in our start or our index. Last time I called it index. Some of you, I was told it was a bit confusing, so we're going to just call it start. And we'll pass start there. And then our next one that we need to pass in will be our new target. So we're going to be updating this target as we go through. And yeah, that's about it. So first up, we have our base case, which is if k equals 2. So I'll just do that here. Base case is if k. Actually, let's do it backwards. Why not? We'll say we'll do our first logic first. So if k is greater than 2, simple enough. What we want to do is introduce our loop. So if k is greater than 2, what we want to do is say for let I equal our start. I is less than our sorted nums dot length. I is incremented. And what we want to do is say stack dot push. And what are we pushing? Sorted nums at I. And then we'll call our function again. So we'll say helper. And then we'll say k is now decremented by 1. Start equals I. Start is +1. We're moving on to our next number. And our new target is new target minus sorted nums at I. Just to update it. And then at the end, of course, what we want to do is stack.pop is revert it back to the original form. Just like in our previous one, we also need to make sure we are avoiding duplicates. So what we want to do is say if our sorted nums at I is equal to sorted nums at I minus 1, we want to continue. And we also need to make sure that our I is greater than our start. So as long as I is greater than our start, so we're not counting for the very first item that we see. We want to do that. So then we stack push and then pop. All right, there we go. And then at the end, yeah, we return. Very good. And then here we'll do our other one, else. So this is where our fun logic comes in. This just gets us to the point of a two-sum problem. So we get our first 2 out, and then we only have 2 remaining. So else, what we want to say is that, how do we do this one? Oh yeah, let left equal start plus 1. No, let left equal, oh yeah, let left equal start. Yeah, let left equal start. Let right equal our sorted nums dot length. And then, yeah, this is where we implement our while loop. So while left is less than right, what we want to do is get our sum. So let cur sum equal sorted nums at left plus sorted nums at right. And then we'll be comparing this sorted nums sum to the new target that we were passing down. So let's see, let cur sum, blah, blah, blah. So we're going to have 3 different options where cur sum is either greater than cur_sum is less than or cur_sum is equal to our new target. So we'll go ahead and do that. If cur_sum is less than our new target, that means we need to increase the value of cur_sum, which means we need to increase our left. Left is plus plus, so we remove a lower number and replace it with a higher number. Else, if we'll want to do, we got to pass in, else if our cur_sum is greater than our new target, what we want to do is decrease our cur_sum. So we have to get rid of the rightmost element, which is our largest number, and replace it with a number that is slightly smaller. So right is decremented. And then else, so this is the case of it equaling our target sum. So what we want to do else, we will say stack.push, and we're going to be pushing our sorted nums at left and our sorted nums at right. We do that. And then what we want to do is output. So we push to our output.push. And what are we pushing? We're pushing our spread out stack. So we need to get, we're making a shallow copy of the stack. If I just put stack, the stack will update every time we change the stack, which is not good. And then what we want to do is stack.pop, and then also stack.pop to get rid of these two numbers we added. And then what we want to do is make sure we move our left and move our right as far as possible to get rid of duplicates and then increment them, or decrement them. So while our sorted nums at left is equal to sorted nums at left plus 1, what we want to do is left plus plus, and another while loop while our sorted nums at right. This is the exact same logic that we used for 2-sum and 3-sum and 3-sum closest. While sorted nums at right equals sorted nums at right minus 1. Let's get our spacing to be consistent. We want to decrement our right minus minus. And then at the end, when you say left plus plus, right minus minus. And we also need to say and left is less than right, and left is less than right, just to make sure we capture that. And then, yeah, else, blah, 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 while loop. And then what we need to do is return. And that should be the logic. I know, pretty deep. Yeah, we go through that. Okay, then we return. Okay, awesome. And then that is inside of our helper. So then what we want to do, like I said before, make sure you always call your helper and then return our output. All right, let's try and go through this one time. We'll use this first one here. 1 and 0. Okay, so first up, we'll order it up. Our input would be, I'll put it here. What would our input be? Our input would be -2, -1, 0, 0, 1, and 2. So that is this one here. That is our sorted version of this. So that is what we're at now. And our target is 0. Okay, very good. And then we'll go through. We initialize our output to an empty array. We initialize our stack to an empty array. And then we initialize our helper. And our start, we will initialize that as 0. And our new target will be initialized as our target just to begin with. So if start is not provided, then it will be 0. If target is not provided, if new target is not provided, then it will be default value of target. Yeah, pretty cool. All right, so here we go. Let's go through this. So blah, 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 blah. We do this, then we call our helper. So right now our k is equal to 4, our start is equal to 0, and our new target is equal to 0. All right, very good. All right, then we say, is k greater than 2? Yes, it is. Okay, so I is now our start. Our start is 0, okay. So here we go. I'll put our I here. All right. And then we push it to our stack. So here, our stack right now will be -2. All right. And then we call helper, we're k minus 1. We're now at a lower level. Start is +1. Okay. New target is minus sorted numbers of I. So that will be a minus, so that would be 2. So our new target is 2. And then we come back up here. Our new I is 1. All right. So k is 3, which is greater than 2. So then we go in here. Our new start is 1. So sorted nums at 1, which would be our -1. So put -1 here. And then we, let's see, k is now equal to 2. Start is now equal to 2. And new target 2 minus -1 would be 3. Sounds good. And then we go through again. K is no longer greater than 2. It is 2. So we'll come down here. So our left is equal to start, which will be our 2. And then sorted nums at length would be our 0, 1, 2, 3, 4, 5. Our 5th. All right, so we look at 2 and our last one. So we have 0 and 2, which would be 2. So here we go. That is our current sum. Is 2 less than our new target? Our new target is 3. Yes, it is. So we say left is incremented. So our new left is 3. And then, okay, so then we get a 0 again. We go through. Okay, yes, our new left is less than, our new sum of 2 is less than our 3. So we go to our 4th element, our spot, index 4, which will be our 1. So then we have 1 plus 2 is 3, okay? So that is our new current sum. It is not less than 3. It is not greater than 3. It is 3. So what we do is push to our stack the left and the right that we have. And then our output, we push the spread out version of this stack. And then we remove the right, we remove the left. And then we have to move our right and our left. So while left is equal to sorted nums, okay, blah, blah, blah. So it is not equal to that, okay. So while sorted nums at right is equal to sorted nums at right minus 1, so 2 is not equal to 1. We'll ignore that. Then we increase left and we decrease right. So now we have our left at 5 and our right at 4. Our left is not less than our right. 5 is not less than 4. So we break out and then we return. And then when we return, we're back to our next layer. So we're back up We're back to 1. We're back to 3. And this is no longer 3, it is 2. Because our target 0 minus 2. And then we move on. And our I increases. So we are now I plus 1, which will be our 0. So that's how this works. Let's go ahead and run it just to see it in action. I'll get rid of these. It should work. Let's go ahead and run it. There's always a chance it doesn't, but you never know. Okay, it does not work. What did we do wrong? Undefined, undefined, undefined. Okay. So -2. Oh my goodness, you know what we did wrong again? This is our class. I need to remind myself not to do this. Remember, if you're 0 indexed, always have your -1. Let's run it again. Every single time. Okay, something is wrong. What is wrong here? Okay. So yes, that is 0. Okay, good. All right, so what is wrong? Let's see, -2. Okay, that's right. All right, what is our input? Let's get this first. All right, let's debug real quick. This is so embarrassing. This has been happening more often than usual. What can I say? So we'll debug. So we have -2, -1, 0, 0, 1, and 2. And our target is 0, 0. Okay. And let's check it out. Okay, so first up we have -2, -1, 1, and 2. That is good. We have -2, 0, 0, and 2. That is good. And then we have -2, 1, 0, 1. 1, 0, 1. Where is it getting this this value at? That's my question. Oh, okay. There we go. It should be I plus 1. So k minus 1, I plus 1, new target. Okay, I think that should solve it. There we go. All right. All these simple mistakes. I was using start, which was giving us duplicates. So if you see duplicates, you probably have an issue with your indexes. And yeah, just make sure you keep an eye out for that. Let's submit it. Run against a large test suite. And we pass. We are better than 23% of people and 26% of people. Yeah, this is the only way I can come up with of doing it. I'm sure there's maybe a mathematical way, but c'est la vie. So yeah, we'll go ahead and move on along to our next question. Our next question is remove nth node from end of list. So given the head of a linked list, remove the nth node from the end of the list and return its head. Okay, so I'm going to be straightforward with you guys. Every time I come across a question like this, I love just creating something called a sentinel node. So const sentinel node. Just call it sentinel. And we'll say new list node with a value of, we don't need a value. And our next would be our head. So this is just a way, in case our head is null, it's easy to do that. And of course, at the end, what we want to do is return our sentinel.next, which would be this head here. So there are two ways of doing this problem. There's an iterative way, an iterative two-pointer way, and then there's also a recursive way. So with the iterative way, first up you initialize a pointer. This will be our fast pointer, and you go through it n times. And then you break out, and then you initialize a new pointer, which is our now head, and then you go through and increment the current and the fast pointer one time until the fast pointer reaches null. And then at that point, you know that you've reached the node you're trying to get rid of. And then you say node.next or current.next is equal to current.next.next. We need to make sure that there is a current.next. And then, yeah, after that, that node that you see has disappeared, and you just return your sentinel.next. So we'll go ahead and we can run through it that way real quick. I know it says it's a medium. It's actually pretty straightforward if you know about 2 pointers and the idea of a fast and a slow pointer. So here we'll say we could do just okay, let fast equal sentinel, and then here we say for let I equals 0, I is less than n, I is incremented. We could do that, and we say fast equals fast.next. Okay, so we have fast equals fast.next. So there's that. And yeah, that would give us a new fast pointer. You could do it that way. We could also use a while, so we can say let count equal n, and we say while count is greater than 0 and fast exists. So in case we reach a null, what we want to do is say that our fast equals fast.next, and then we decrement our count. Count is decremented. That's another way of doing it. I don't know if it says there's a chance that, okay, there's only 30 nodes. So, 0 of 1, pretty cool, guaranteed. More or less. Okay, so there we go. We get our fast pointer, we get our slow pointer. So it could be equal to SC. So we don't really need that, actually. So we'll just go ahead and use our for loop. For let I equal 0, I is less than n, I is incremented, and then we say our fast equals fast.next. And then over here, we will create a new one. So we say let cur. So this will be our sentinel. And then down here, what we want to do is go through. So while we have a fast, what we want to do is say fast equals fast.next, and our cur equals cur.next. So we're just going through all of these. And then at the end, what we want to do is say cur.next, because we'll stop when we get to the end. So cur.next is equal to cur.next. Just to make sure we do have something to point to. We should, but you never know. And then what we want to do is just return our sentinel.next. So yeah, pretty straightforward with the iterative approach. Let's see, so fast is our sentinel. We increase it n times to get our fast pointer in the right place. Then we initialize our cur pointer. And then what we do is say while our fast exists, it is not null. We say fast equals fast.next and cur equals cur.next. We just move forward until our fast reaches the end, and at that point we are n numbers away, and then we say cur.next equals cur.next.next. So basically we just skip that, and then we return simple not next. My only issue, we could probably test it out verbally, but we're running out of time. I'm not too sure if I stop at the right place. We'll run it. There's a chance. Okay, here we go. Type error. 950 value. Next undefined. Where? Okay. 950. Oh, la, 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 la. Okay. 2, 3, 4, 5. Let's see. What is wrong here? Turn sentinel is a new list node. Okay, this.next. Because we don't need our value. What do we, okay, our output. Okay. So we'll say while fast.next. So we have to stop one early. Run it again. There we go, and we pass. Yeah. So we stopped one early specifically for, I got my math wrong a little bit. So this would actually put us at the element that we need to remove, not the one before it. So we need to stop one ahead. So that's why I say fast.next. We could do that. Another way of doing that would just to be n minus 1. Really? We could do that. But yeah, pretty fun, pretty straightforward. Let's run it against a large test suite. And what do we get? We're better than 6.3%, but our memory is pretty good. I told you there's another way of doing it recursively, but this video is getting pretty long. Maybe I can talk about it next time if I remember. If not, too bad. So here's my iterative approach. Hope it helped you out. Hope you understand what I'm talking about. If you have any questions, put them below, and I'll do my best to help you. Have a great day. Catch you later.